Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 4.20. I had a request from a reviewer to take a look at this problem and give my approach as to how I would tackle it. So I start off here with a diagram, and I'll go ahead and read the problem statement. Wet air containing 4.0 mole % water vapor is passed through a column of calcium chloride pellets. The pellets absorb 97% of the water and none of the other constituents of the air. The column packing was initially dry and has a mass of 3.40 kilograms following 5.0 hours of operation. The pellets are reweighed and found to have a mass of 3.54 kilograms. Part A, calculate the molar flow rate in moles per hour of the feed gas and the mole fraction of water vapor in the product gas. Okay, so we've got our column here, got water coming in through here, and it kind of fills up the calcium salt that's in there, and then it comes out a little bit less wet than it came in. Okay, here are some of the things that they gave to us in the problem statement. Well, we have how much water is going in minus how much water is going out is accumulating inside of here. So I'll just put that as A. A is the accumulation rate. It's not the total amount of accumulation, it's the accumulation rate. This is the rate at which water enters, this is the rate at which it leaves, and this is the rate at which it accumulates inside of the column. Okay? We know that this accumulation rate is 0.97% of the water that goes in. They gave that to us. And then they also gave us a way to calculate how much water that was. So they said they weighed how much calcium salt there was before and after, and it was a little bit heavier, obviously, afterwards because there's some water in it now. And then they told us the total amount of time it took for that to happen. Okay, so they gave us two ways to calculate A. This is the first way, and then this is the second way. Okay, so let's go ahead and calculate A. A, we have the mass flow rate. We have the difference in the masses over the difference in time. And the difference in masses, difference in time. That's the mass flow rate, so we need to convert that into a molar flow rate. So we have this conversion here, and we get 1.33 moles per hour. Okay, so that's the first step. Now we've calculated an actual number for what A is based off of the information that they gave us here. Okay, let's take a look and start doing we already did a water balance here where we said, okay, this is how much water we have going in, how much we have coming out, and how much is accumulating. Then we also have that our accumulation rate is this. Okay, so let's put these equations equal to each other, and now we have one equation here, and we can combine like terms and simplify this a little bit, and we get one equation based off of our water balance. Now let's move on to the air balance. Okay, we have an air balance here, a certain amount of air going in, and it equals the amount of air going out. Okay, then we substitute in the things that we know. We want to solve for the mass fraction of water, so I just put in the mass fraction of water right there, then we kind of are stuck with that. That's about as far as we can go with the air balance because we don't know the flow rates going in or out, and now we have it in terms of the water like we're trying to solve for. Okay, so we'll do one more balance. Here we'll do the total mass balance. We'll say the amount of mass going in minus the amount of mass going out is equal to the amount of mass getting accumulated. Now this is not an independent equation because we already used water and we already used air. Okay, so using the total is not an independent equation. If we tried to substitute this information into one of these equations and solve for the unknowns, you would get something that doesn't work. It would just cancel out. You'd end up with something trivial like 1 equals 1 or 0 equals 0 or something like that, because the equations are not independent. In order to make them independent, we have to use the information right here that we solved for earlier. We know that A equals 1.33 moles per hour. Okay, so if we substitute in that A equals 1.33 moles per hour, and we know what A equals, now it's an independent equation. Okay, so we'll leave A as is when we're solving things, but we'll keep in mind that A is this, and this came from independent information. Okay, so now it's an independent equation, and we can move on. We have 3 equations here, highlighted in red, and we have 3 unknowns. So we can solve for the 3 equations and 3 unknowns using substitution or whatever method you want to use. I went ahead and used substitution. You guys can follow along. So first, I got rid of N2 because they asked for N1 as one of the deliverables. So if we substitute all of our N2s with N1s using this equation, then we'll be able to solve for N1. Okay, so that's what I did here. And I substituted in N1 for N2 here, using our 2 other equations that we have here and here. And then I starting with this equation, I start crunching the numbers and moving terms around until I get something that says xw2 equals something in N1. So all of these are known, but we need to solve for N1. So now we substitute xw2 into this equation and we solve for N1. You guys should be familiar with this. Here's a little trick that I found. So after I did the substitution, I said, hey, this term looks really similar to this term. Is there a way for me to cancel these out? And there is. If you take the negative sign and you put it down under here, you can swap the order of those and then they match up and you can just cancel them out. It makes the math a lot easier, so you don't have to spend so much time on your calculator. But all right, so then we cancel out to this equation and we get that N1 equals this, and finally N1 equals 34.3. Okay. Then we can substitute our number for N1 back into this equation, and we calculate that xw2 equals 1.25 times 10 to the negative 3. So we've solved for the 2 things that they asked us for here, just using substitution and using our 3 sets of equations that they gave to us. Okay, so for part B, the mole fraction of water in the product gas is monitored and found to have the value calculated in part A for the first 10 hours of operation. But then it begins to increase. What is the most likely cause of the increase? If the process continues to run, what will the mole fraction of the water in the product gas eventually be? Okay, so we have a certain capacity for water to accumulate in the salt. Once the salt has reached its max capacity for holding onto water, it'll just stop grabbing onto the water. Okay, so if the water stops grabbing on to the salt, then the water that goes in just comes right back out. So if the water that goes in just comes right back out, then it's not going to change in concentration. Okay, so the mass fraction of water as time goes to infinity, the mass fraction of water in the exit stream just becomes the same as it was in the inlet. It doesn't go more than the inlet, it isn't less than the inlet, it just asymptotically approaches the same value as the inlet. All right. Well, that is it for problem number 4.20. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.